Hello again. We are going to continue on chapter 7. I hope you're doing fine. So let us get started on identities and how to verify them. So we're going to continue with sum and difference identities by first proving just one of them, which is this one right here. So what is cosine alpha minus beta? Now we know you're mathematically mature enough to know that this is not cosine alpha minus cosine beta, okay? So I'm not going to even talk about that. Well, I kind of did, but not anymore. So what is cosine alpha minus beta? So to prove that, to see what it is, we're going to make an alpha here, right? An angle alpha, and put a point here on the unit circle, and call it cosine alpha, it's missing there, comma sine alpha, right? So this point right here is basically, let me rewrite it here. So is cosine alpha sine alpha, okay? That's what that is. So now we're going to create another point by making a angle beta here, right here. And we know, according to the definition we have for unit circle, that's cosine beta, sine beta, the coordinates, right? Now, we also create this point here such that this angle right here is alpha minus beta, okay? So if alpha is 110 and beta is 30, then we make this 110 minus 30, right? Which is like 80 degrees. Whatever alpha is, we make this alpha minus beta. And we know that this angle here is also alpha minus beta. How do we know that? Well, because this is alpha, and if you take away beta from it, you get this angle. So that means this chord here, which is called a chord, it's like a segment, that connecting 2 points on a circle is a chord, and the biggest chord, of course, is the diameter. So that segment or chord is the same as this one because the central angles are the same, right? So what do? We write distance formula. So we write, remember this was an alpha here that I missed. So we use distance formula to write the distance from here to here and from here to here. And we know distance formula is like, if you have 2 points, x1, y1, and x2, y2, then it's x2 minus x1 squared plus y2 minus y1 squared, and then you take square root. So to write the distance from here to here, we write the square root of cosine alpha, if you assume this is x2, this is y2, and this is x1, y1. So we have cosine alpha minus cosine beta squared, and then sine alpha minus sine beta squared. And for this one, we assume that this is x2, this is y2, this is x1 and y1. So it would be cosine alpha minus beta minus 1 squared plus sine alpha minus beta minus 0 squared. Okay? All right, now we're going to work with that expression, do a little bit of algebraic and trigonometric acrobatics here to simplify that. So first of all, we raise both sides to second power to get rid of the square roots. They come out. And then we have to square each of these, right? And to square, everybody knows, I think, again, you're mathematically mature enough to know that this is a squared minus 2ab plus b squared. And a plus b is a squared plus 2ab plus b squared. So here, a is cosine alpha, b is cosine beta, so we get this. Over here, a is sine alpha, b is sine beta, so we get this. Over here, a is this, and b is 1, so we get this. And over here we have A is that and B is 0. So we just have sine squared, sine alpha minus beta squared. Okay? All right, now if we continue the simplification process, we end up with canceling, well, not canceling, but cosine squared and sine squared alpha, that's 1. Cosine squared beta and sine squared beta, that's another 1. So that's 1 and 1 that you see over here. And then the rest of it we just rewrite. On the red part, on the right part, we got this one and this one. The alpha minus beta part is the same. So we add them, you get 1. So that's 1, 1 right here. And then 1 squared is 1, so that's another 1. Okay, so we get the black side equal to red side, and then we have 2 1s here, so that's a 2, and there's a 2 here, they cancel each other. Okay, now we divide by -2 on both sides, and we get the formula for what? For cosine alpha minus beta. So we got the cosine alpha minus beta formula, and now we can continue. Now, cosine minus alpha, we have a formula. So how, you don't have to memorize these, but you know, they used to make people memorize them. They made me memorize everything. But if you have a way to memorize it quickly, do it. If not, gradually you remember some of these when you practice with them. Memorizing them doesn't give you any advantage really. But if you memorize it automatically, yes, that means you have done enough practice, right? But if you don't remember which one is plus, which one is minus, you could just look at the formula chart for identities. Now, how do we prove alpha plus beta? What is the formula for that? Well, now we can use our knowledge. Instead of writing A plus beta, we can write A alpha plus beta. We can write alpha minus negative beta and use the same formula, right? So if you do that, well, cosine negative beta is the same as cosine beta, and sine of negative beta is minus sine beta, so this changes to minus. So we got a new formula for cosine alpha plus beta. All right, so here's an example. Let's say using the formula for cosine of the difference of two angles, find the exact value of cosine 5 pi over 4 minus pi over 6. So what we do, we use the formula and write this in this form, obviously, right? And we know cosine 5 pi over 4. You know that because you know what? 5 pi over 4 ends up being here. And you know it's the same as pi over 4 by, at this point, you know how to do that because the reference angle is pi over 4. So the cosine of it is negative cosine pi over 4, right? And cosine pi over 6, you memorize, you know it's square root of 3 over 2. Sine of 5 pi over 4 is negative of sine of pi over 4, right, as you see. So it's negative square root of, so that makes that minus, right? And then sine pi over 6 is, of course, 1/2. And you combine these, you multiply, you get square root of 6 over 4 minus the square root of 2 over 4. And then we have the same denominator. So this is the exact value of that, right? And that's how we use that identity. All right, what about sine alpha minus beta and sine alpha plus beta? How do we prove that? Well, we can use our knowledge that if two angles add up to 90, remember, then cosine of one equals to sine of the other, and also sine of one equals to cosine of the other, right? So if I want sine of, let's say, alpha plus beta, I can write it as a cosine and use the cosine formulas. So I can write it as cosine of what plus alpha plus beta gives me 90. Well, I take 90 and subtract a plus beta from it. So this angle here, if added to this angle, you get 90. That means sine of one equals to cosine of the other, right? So instead of doing this, we can do this, which we know how to do, because if I apply the minus, this would be cosine minus 90 minus alpha minus beta. And we know this, an angle minus an angle, right here. That's the formula for it. So it's going to be cosine of the first one times cosine of the second, right? Plus sine of the first one times the sine of the second. Okay, now again, cosine 90 minus alpha, remember this angle and this angle add up to 90. So cosine of one equals the sine of the other. So this is the same as sine of alpha. And we leave that as cosine beta. Again, sine of this is the same as cosine of this. Why? Because they add up to what? They add up to 90. So now we have a formula for what? For sine alpha plus beta, which is right there in the chart, right? And sine of alpha minus beta, you can just write it again as sine of alpha plus negative beta and use the plus one that we just found, right? This one. And we do that and we find the formula for sine of alpha minus beta, which is sine alpha cosine beta minus cosine alpha sine beta. All right, so these are four formulas for sum and difference of two angles. All right, so that's all there is to it. Here is an example. Verify the following identity, that this equals to that. So remember we talked about identities, right? Now, the two identities, when you write an identity, this identity is true in the domains of the expressions involved, right? So that means the left side and the right side may have two different domains, right? But for this to be true, the domain for this expression, this equality to be true, would be the intersection of the domains of left side and the right side. We are not talking about that here, but you have to take that into account when you do this. Remember, when you modify an expression in trigonometry, the stuff that you do, things might get canceled, it's going to look very different, so the domain changes, not all the time, but most of the times. And when we write an identity, this identity is true in the domains of the variables involved, of course, and that would be the intersection if you wanted to use it. Like if this is a function, this is another function, the domains may be different. Okay, now let's see, here we go. So we start from left and we use the formulas. Obviously that has sine of alpha minus beta, and we have a formula for it here, so we use the formula to expand it. And as you see, this is a common denominator, so you can put it as this over this minus this over this, and then things get canceled and we get tangent alpha minus tangent beta. So they're useful in simplifying expressions. Okay, this is probably most better simplified, is a better expression to work with than this one, right? All right, so here is another example. Find the exact value of cosine 75. So we have to, of course, we don't do this anymore unless we want to simplify expressions. But these formulas were used to find values of angles that were kind of sum or difference of angles that we knew, right? the values of. So instead of finding cosine 75, can we find sine and cosine of 45 and 30 that we already know? Yes, we use the formula. So we write it as 45 plus 30, and we use this cosine of alpha plus beta formula. And then we put the values there, then do the operations, and we get the answer. So that's the exact answer for that. Now, of course, if you put this in the calculator, you get a decimal answer. That's not what we want. We want to practice using these formulas and get exact answer, right? All right, here's another example. Use the sum or difference and difference identities to evaluate sine of 45 minus 30, which is sine of 15 degrees, right? So instead of finding sine of 15 degrees, we can find a combination of sine and cosine of 45 and 30 that we know. We memorize them, remember? So sine of 45 minus 30, again, we use this formula, sine alpha minus beta. And we put the values there. And we have an answer. So you can stop the video and follow this and make sure, you can get this. It's really not that hard. It's a little bit of arithmetic. All right. So finding the exact value of expression, use the exact value find the exact value of this. Let's make it fine. Okay. Now, what is the exact value of this? Well, we're going to think of this as an angle and think of this as an angle. Remember, sine inverse and cosine inverse actually is, the answer to these is an angle, right? So we assume that this is an angle alpha and this is an angle beta. But remember the question that this asks us to answer. The question is, what's an angle? Let's call it alpha. So what's an angle alpha in where? In the restricted domain of cosine from 0 to pi. So what's an angle alpha in the restricted domain of cosine 0 to pi that has cosine 1/2? Okay? So restricted domain of cosine is 0 to pi. So cosine alpha is 1/2, and we're looking from 0 to pi, right? And the other one, let's say call it beta. So the other one is, the question is, what's an angle beta in the restricted domain of sine, which is over here, from 90 to negative 90, right? Whose sine is 3 over 5. So sine of beta is 3 over 5, right? So we know cosine alpha is 1/2. We know sine beta is 3 over 5, right? So we can use Pythagorean identity to find what? To find the unknown quantities that we mean. When we use the formula for sine alpha plus beta, we end up with what? We end up with sine alpha times cosine beta plus cosine alpha times cosine beta. And you see we are given cosine alpha, but we don't have sine alpha. And we are given sine beta, but we don't have cosine beta, right? So what we do, we use Pythagorean identities for alpha and beta to find the unknowns that we're looking for. So as you see, sine alpha would be plus and minus the square root of 3 over 2, and cosine beta is plus and minus 4 over 5. But remember, alpha is in this area, and in that area, what is sine? Sine is positive, right? So we have to pick this positive value. And for cosine beta, remember where beta is. Beta is in this area right here. And we know cosine is positive here. So we pick the positive value for cosine as well. So in both cases, we pick the positive value. And then we put it here, including the two numbers that we have, 1/2 and 3/5. and we multiply and we get that. Okay? So that's how we deal with that. All right, you can, again, stop the video and follow this and make sure you understand how we got that. Okay? So we assume that this thing is sine of alpha plus beta when alpha is this and beta is this, right? All right. So derive a formula for tangent alpha plus beta in terms of tangent alpha and tangent beta. So we know tangent alpha plus beta is sine alpha plus beta over cosine alpha plus beta. And we know what these are. We just, saw the formulas. So we'll put them there. So that's the answer. But we don't want that. We want it to be in terms of tangent alpha and tangent beta. Well, to do that, we have to use, again, some trigonometric and algebraic acrobatics here, right? So what do we do here to make this tangent? Well, think about it. We say, okay, if I had cosine alpha here below sine alpha, that would be tangent alpha. So, and here also, how do we make this tangent? Maybe we can have a cosine beta at the bottom. So why don't we multiply the numerator by 1 over cosine alpha cosine beta? That's what we need to make these tangents, right? And we do the same over here, but we are not going to be able to make this to be to have one tangent here. We're going to have two tangents, as you see. So let's do that. Multiply this by that, multiply this by this, multiply this by that, multiply this by this. We get this, right? And here, you see the cosines go away. Over here, these cosines go away. So that's the tangent alpha, that's tangent beta. Over here, these cosines go away. And these cosines go away, we just get 1. So that's 1. Over here, nothing goes away, but we can separate it into two fractions, tangent alpha, tangent beta. And now we have a formula in terms of tangent alpha and tangent beta, as you see. So that's tangent alpha plus beta. And to find tangent alpha minus beta, again, we use this trick, alpha plus negative beta. And we know tangent of negative beta would be negative tangent beta. And over here too, right, tangent of negative beta is negative tangent beta, so it makes this positive and makes this negative. So again, if you want to find a way to memorize these, you could, but if you use them gradually, you kind of memorize them. But until that time, you use a formula chart, which is the identity charts, and you can find those in the textbook, or you can search for trig identities chart, and you can get 10 million hits in internet. Okay? So now, example, find tangent alpha plus beta given that sine of alpha is 3 over 5 and alpha is the first quadrant and cosine beta is negative 5 over 13 and beta is in the third quadrant, right? Okay, well, we graph them. So alpha is an angle in the first quadrant such that we use the second definition, right? This is y, and this is r and y. So we're going to put it here. So the y value of this is 3, and r is 5, which is this distance right here, right? So if this is 3 and this is 5, then we can find the x value here, right? Easily. So x squared plus y squared is r squared, so x is positive 4 here. So x is 4, r is 5, and y is 3, right? All right, now from here, we can find whatever we have in the formula. To see the formula, tangent alpha plus beta involves tangent alpha, which we have. It involves tangent tangent alpha, which we don't have, and tangent beta, which we don't have. So from this right here, this relates to alpha. We're going to find tangent alpha. Well, tangent is what? Tangent is y over x. So tangent is 3. So tangent is going to be, tangent of alpha is 3 over 4, right? 3 over 4, y over x. So that's tangent alpha. Now, to deal with beta, again, we do the same thing we did here. This time, the x is -5, right? Because cosine of beta is given. So this is x, and this is r. So x is -5. X is -5. R is 13. So what is y? Well, y is -12. Right? -12. So what is tangent beta is going to be -12, which is y, over -5, which is x. So tangent beta is 12 over 5. Well, now we have everything, right? So we're going to deal with alpha, two separate angles, right? So now we have all the values we need. We got, tangent alpha, tangent beta, tangent alpha, tangent beta. We just do some arithmetic here. We end up with -63 over 60. Okay? Again, stop the video and follow this one more time. Make sure you get the same answer. Co-function identities. We talked about this already. We said that if two angles add up to 90, then function of one equals to co-function of the other, right? And I think you remember that already. So it says verify the identity cosine pi over 2 minus theta equals to sine. Now, we know this is true, but we want to verify them. Well, this plus that is 90, so obviously cosine of one equals to sine of the other. But we want to use the formulas we just talked about to prove this. So what's cosine alpha minus theta, minus, here alpha is pi over 2 and beta is theta. So cosine, cosine, sine, sine, and the sine is opposite. So what's cosine pi over 2? 0. What's sine pi over 2? 1. So the answer is sine theta, as you see. Okay, again, stop the video if you want to practice with this yourself. Here's an application problem I want to do. So rigid rod with length 10 centimeter, this right here, which is this right here, 10 centimeters, is connected to this piston, and the piston is allowed to move like you see in this animation. And we want to know the point B is able to freely move along the horizontal, right? This B, deriving a piston. If the wheel rotates counterclockwise at 4 revolutions per second, find the location of point B as a function of time. So we want to find the location of this point as a function of time. So let's do that. So we're going to consider that to be a right triangle. Now there's a connection between B10 and this side, and know that the radius here is 4 centimeter. So we know that A is really cosine R cosine theta and R sine theta, right? And R. Now here we are going to have to the angle to the linear velocity here, which is what? Which is 4 revolutions per second. So let's do that. So Now, what is the linear velocity? Is 4 revolutions, here you go, omega is 4 revolutions per second. But we want it in radian. So each revolution is 2 pi radian. So we write here 2 pi radian over revolution, 1 revolution, and the revolutions go away. And the radian is like a number, so we don't really say it because, so omega here would be just the unit of what? The radius, whatever. There is how much radian I meant. Radian per second, right? But when we multiply by the radius here, right? This becomes what? The unit of just centimeter, right? Whatever that is. So this distance here is going to be in centimeter, and this distance would be in centimeter. So this is sine, and this is cosine, right? From here to here is cosine, and from here to here is sine. But we are interested in this distance right here, right? Why? Because in this right triangle, we want to relate these 3 sides so we can get an expression for b, this distance that changes as this goes around, right? This right triangle changes. That's what we want to do. We want to write this in terms of time, not in terms of angle. So if we know how fast this thing is going around, then we can multiply the linear velocity by time to make it how much angle, right? If you go 55 miles per hour and you do this in 2 hours, well, then the hour and hour cancels, you go 110 miles, right? So if you go 50 miles per hour for 2 hours, you do 110 miles. So if you do 8 pi radian per second for, let's say, 2 seconds, then you go 16 pi radians, right? So it becomes an angle. So linear velocity times time gives you basically how much angle, right? Remember, omega is theta over t, right? The angle would be omega times t. So that's omega times t right there. That's why we put, instead of cosine of theta here, we just put 8 pi t because that is the angle. All right, now we're ready to write an expression for b. Is a right triangle, b squared plus this squared equals to 10 squared. There. And we isolate b, and you see b is going to be a function of t. So we're going to call it f of t, right? And this is, so this is b, right? That's the b part of it, but we wanted the distance from what? From here, right, to here. And we know from here to here is that cosine, right? And the distance from here to here is b, so we can add them. B plus this part gives you the distance over here. As this b goes, derives the piston back and forth, we know this distance changes according to what? According to this expression. So I wanted just to show you an example of how we use trigonometry in application problems to write expressions that govern the movement of that point, right? Goes back and forth. All right, so again, stop this and see if it made sense here. Understand that how we got that theta there, and also how this point is r cosine theta or sine theta. And remember, we're writing the distance from here to that point. So we take that b and write an expression for it, and then add that part to it. All right. Now, some more application problems. We can think of the slope of a line as tangent theta where theta in negative 90 to 90 in this area is the angle that the line makes with x-axis. For example, let's say in algebra we have a line f of x equals to 2x, this line right here. Now, in negative 90 to 90, what angle does it make with the x-axis? Well, this one, right? Now, you might say, no, is this angle? And I say no, because I said from negative 90 to 90. So you cannot pick this one. You have to pick this one, right? So you might say, is this one? Well, no, that's not what I want. I want this one, right? From 90 to negative 90, that means with the positive x-axis, right? Okay, so that's the angle. So what I'm saying is that the slope of a line that we find is related to the angle that the line makes, this black line makes with the positive x-axis, which is 63.43.95. It's not an exact number. It's an irrational number, the angle. So what we get is, we know the slope is 2, and if you find tangent of this angle, you get 2. Now, it would be rounding error here. It's not going to be exactly 2. It would be 2.000 something or 1.9999 something, because this is not the exact angle. It's approximated. But this formula that the slope, which is delta y over delta x, remember delta y is change in y over change in x, that's the tangent, obviously, right, of this angle. And for the red one, the same thing. The angle that it makes is negative. It should be negative here, 63 something. And if you put the slope, tangent of negative 63 point something would be negative 2, which is the slope of this line, right? All right, so that's the connection between the slope and tangent of the angle that the line makes with the positive x-axis. All right, so now it says, let L1 and L2 denote two non-vertical intersecting lines, like these two, non-vertical intersecting. And let theta denote the angle between L1 and L2, which is this right here. Show that tangent of theta is m2 minus m1 over 1 plus m1 plus m times m1 times m2. That means you can find the angle between two lines if you have their slopes, which is a pretty good formula to have. If you want to find the angle of two lines intersecting, this is how you can find it. Tangent of that angle is basically a slope of one of them minus the other one over 1 plus the product of their slopes. So by moving L2, as in the figure here, you see if I move L2 over here, you see that this angle right here is actually theta 1, and this angle right here is theta 2. So the angle that they make, right, the angle that they make here, this angle here, is theta 1, which becomes this one if I move this over here. So this theta here is theta 2 minus theta 1, right? It may not be obvious when they're in that position, but if you move this red one over here, put it over here, then you see that the angle that they make is actually theta 2 minus theta 1. All right, and we know the formula for tangent of alpha minus beta, so we use that. And since we talked about that tangent is actually the slope, right, delta y over delta x, so we can replace these with the slopes, and we have that. So we proved that. Given that tangent theta 1 is actually delta y over delta x, and tangent theta 2 is delta y over delta x for the blue line. Okay, so I'm going to continue with this chapter, and I'm going to stop the video now and come back here. I have the sun in my eyes. Here you go. So I see you in the next video, okay? Take care of yourself and others. Oops. Let me cancel that.